All right. Good morning or good afternoon, everybody, depending on the case. And welcome to this webinar on validating frequency decomposition results using forward modeling and how we can correlate geology to frequency. The cognitive workflow at the heart of GeoTeric is centered around reveal, interpret, validate. And it is applied throughout the software, enabling users to understand the geology through the attributes analysis, to interpret what they see in the color blends, and rapidly and efficiently, and now to validate that interpretation and model using our new validate module. So in terms of the case study that I'm showing you today, is going to be centered on the Stybarrow reservoir on the northwest shelf of Australia. The Stybarrow oil discovery was made in February of 2003 with the Stybarrow 1 well, followed by Stybarrow 2 in the same year to confirm the up-deep extent of the reservoir, and then Stybarrow 3 to determine the oil-water contact and confirm the down-deep extension of the reservoir. In terms of the amplitude extraction, the reservoir is characterized by a bright spot, so high amplitudes. This is the top of the reservoir horizon mapped with the amplitude extraction, so you can see the dimming of the amplitudes on the down deep section of the reservoir, and the number 1 well, which was the discovery, the number 2, and the proposed location for the number 3 right after the dimming of the amplitudes. So the theory is that this dimming of the amplitudes is due to the presence of water. So that's why they chose that location to test the oil water contact. And this is the arbitrary line that we see here going through Stybarrow 2, 1, and 3. So that's the reservoir level. And we can see the dimming of the amplitudes at the proposed Stybarrow 3 location. In terms of frequency decomposition and the color blending, the reservoir is also characterized by a strong response from the 3 frequencies at the same time. So you got the whitish colors, and at the area where the amplitudes dim, we also have a dimming of the frequency responses, and that's the proposed location for the Stybarrow 3. So the question relating to frequency is that with this dimming of the amplitude of the frequency responses due to the change in the fluid content, is it the changing of the reservoir geometry, or is it lithology changing? So that's kind of the 3 reasons that we point out for the changes in frequency response. But with Validate, we'll be able to test those scenarios. So we will build a model like this with the reservoir thinning out below this channel location here. And we will test several hypotheses for changing properties at the reservoir section under the channel. The workflow that we followed through the case study was we took the original data, we did our frequency decomposition and our color blends directly from the original data, and then we went back and built our model, extracted our wavelet from the data, and fill our model with rock properties, generating the synthetic. This is an iterative process, so we can change our rock properties until we get a good match between the synthetic and the original data. And then we will apply the same parameters for the frequency decomposition and the color blends. And then we can compare both color blends, the one coming from the synthetic, from the model, and the other one coming from the original. And we will tweak the rock properties until we get a good match between the two, that way linking the frequency responses with rock properties. So where we got the rock properties to populate the model was a bit more tricky. So in time, this case study sits right before they drill Stybarrow 3, but in the present day, this field is already decommissioned, so the abandonment phase is already started, and they drilled a total of 12 wells. So we do have information from Stivero 3 and all the other wells. So to populate the model, we had two problems. First, testing the theory that the changes in frequency and amplitude are due to water, presence of water in the reservoir. Ideally, we would do a fluid substitution in the area where we have the dimming of the amplitudes, but we don't have all the information to do that. So we took the rock properties from the Stivero 3 well, where we know that there was a water sample collected at this depth here so that's the gamma ray log. And so that's the base of the reservoir or the sands. And that's the location of the first water sample taken. So we've defined that interval, so where they recovered the water sample and the base of the sands as our properties to take out for the reservoir filled with water section. The channel was also a challenge. Ideally, again, we would use an analog. Since we don't have any analog or access to one, we came back again to Stivero 3, and so that's the top of the channel. So we use that interval from the top of the channel to the base of the top of the sand interval to define the location or to take the properties for the channel. All other rock properties were taken from Stivero 1. In terms of what was found in the wells, so Stivero 1, a good sand interval, good quality sands, 27% porosity, all filled with oil. Stivero 2 was also encountered a thicker package of sands, also all filled with oil. There's no gas cap. And in terms of Stivero 3, there was much thinner, so only 2.1 meters of oil-bearing sands. And with this main interval here, there were several intervals with that were oil-bearing, but the majority of the sands are not reservoir quality. Porosity is too low. So in terms of what we did, for the demo, so the way to activate, validate is through the top right bar. So we give it a name for our section, the session, and use one of the seismic volumes as a starting point. This opens this window where we can go to our, in this case, a cross line where I know the location of the reservoir. So we zoom in the area of the reservoir, and now we are going to define the area where we are going to work on. So that's, you define a rectangle around the area of interest, and that's the area where we're going to work. So to define the layers, we can start with the interpretation that we already have. So we overlay the horizons and use them as a seed point to make our initial model. Let's take this off, and then we can edit those points. So my reservoir disappears under the channel here, so I edit that point and delete that one, so I get the proper geometry for the layer. And then I'm going to manually add my channel and segment my reservoir in the area where the amplitudes dim out, and I'm going to follow that reflector as the top of my channel. In this way, I'll define 2 more layers. So the area in blue is where we will change the rock properties and simulate having the water. So we take the properties from the wells. So the light green will be our overburden. The dark green is our seal. The red will be taking the properties from the #1 well at the reservoir level. So that's reservoir with oil. Below the reservoir, we'll take that as the underburden. Then the light green will be the channel where we took the properties from the number 3 well, and the blue is the reservoir section filled with water. So all of these properties are being taken out from the wells. You can use a library of properties that you already have, or you can use VPVS and density logs to extract the properties using depth or time ranges. Or you can use markers on the wells as well to define that. And this is why we do the fluid substitution as well, but we didn't have all the properties to do that. So next we go to the forward modeling, where we convolved our model with the wavelet. It can be a standard breaker, or you can extract the wavelet from the seismic. In this case, was extracted along the Stibaro 3 well path. And then you get your synthetic. So in here we start to see that we have a good geometry. You can put on the wiggle traces to QC the results. There's also a correlation, so we can define an area, and we can see here that there's a good correlation between the synthetic and the original data. And we can see a dimming at the location where we have the water. So then the next phase will be the frequency decomposition. So I'm going to use the same frequency bands that I used for the original blend. It's a constant Q, and we choose our blend to take out the automatically the scaling that was applied. And then we can compare our blends from the synthetic, which is this one, with the real one, or the original data one that is on the background. So we can see that although there's the dimming of the amplitudes, dimming of the frequencies, it's not the same as the original, and the colors don't match as well. And this is the scenario where we have water on that section of the reservoir. So now we can change the properties at that location. So I'm going to link the blue layer with the red one. So now all properties are coming from the reservoir filled with oil at the number 1 well. And we can see that we have a much stronger dimming at that location. So that's with water, this is with oil. And we start to see the same kind of color variation, same intensity variations as we see on the original data. So looking at the variable density, same thing, a much stronger dimming of the amplitude. So that's with water here, and now with oil. So the conclusion from changing these rock properties and looking at the blends and the frequency decomposition is that, so for the number 3 well, the main objective was to find the oil-water contact and confirm the extent, the down-deep extent of the reservoir. The location of the well was based on the dimming of the amplitudes on the reflectivity data, and the RGB color blends from frequency decomposition also show a dimming at that location. But the forward modeling work that we did suggests that the factor that's giving more weight to the frequency decomposition results, it's the thinning of the reservoir and not a fluid change. Excuse me. So our interpretation is that the channel eroded the reservoir at that location, resulting in a thinner sand interval. And is that change of thickness that's producing, or is the change in amplitude and the change in frequency response, it's not just due to the presence of water or fluid change, it's a combined effect. So if this kind of tools and workflow was available at the time, they would probably be able to de-risk the location of Stibaro 3 much better, and possibly even avoid drilling of Stibaro 4, which was drilled as a sidetrack from 3 because they didn't find it. They did not find the oil-water contact with Stibaro 3, so they had to do a sidetrack Stibaro 4 to find and confirm that oil-water contact. So if this was available at the time, they would probably be able to de-risk the Stibaro 3 location much better, and again, possibly avoiding drilling Stibaro 4. And so that's all for me. If you have any questions, please type them on the chat box, I think. We do have a fluid substitution tool. So if I go to rock properties, so in here on fluid substitution, so if you fill in, I can't show you because I don't have all the information here. So if you fill in the necessary well logs and the properties that we need, there will be a two-way bar here at the ends where you can use a slider with different mix of gas, oil, and then on this side mixes of oil, water. So through the fluid substitution, yes, you'll be able to recognize differences between those two mixtures, so oil, water, or oil, gas, that way. But we couldn't do that because we didn't have all the information from, so I went through the well reports and I could not find the bulk modulus. So that was the only thing missing to do this properly. Yes, so in terms of the workflow, sharing the workflow, yes, so if you send me an email to, I'll write my contact here. So my email is hugo.garcia@geoteric.com. So send me an email and I'll share that with you. Right, if you come up with any more questions, just shoot me an email and I'll do my best to answer. So